You should be good.
Hello, good morning. Midterm X. And as a homework due on the same day. And since it is right on the day, I give a little extra buffer, so that it will be available until 24 hours or so. You can submit it later. Extra buffer, I think. Is that a correct word? Is that clear? So in case you feel that exam more important, I don't know to do it. So don't spend all your time on the homework, but it's not infinite extra time. And the style of the exam, what is expected, is all remains the same, pretty much, very much like the first exam. So the expectation is that there will be about 8 questions, like between 7 to 9. That's how I try to do that. Probably what it's going to be, and it will cover. When you study, it will cover most of the concepts between the midterm 1 and midterm 2. But having said that, remember most of these concepts are dependent on what we studied earlier. So it doesn't mean that everything else you can ignore. So things are built on one from the other. So any comments or questions you would like to ask about the exam or the format, anything? And everything we cover today and Thursday will also be included in the exam. Unlike midterm 1, we will not have a review session. I did notice that the review session was very useful to all of you. But at the same time, I also get the impression that you guys are feeling more comfortable with the concepts we have studied after midterm 1. It seems like you find it simpler. So, and I usually do not do a review session, so I decided not. Is that a strong opposition to that? Is there a strong recommendations for a review session? Oh, what I can suggest is the following. Yeah, how about this? There is so we have an exam on Tuesday. If you really think the review session helps significantly, there is the course 206B, which is the tutorial section for that. A few of you enroll for that, and some of you come and sit in it. So I'm not saying I will use that as a review session and that is necessary. That's not part of the course. But if you really feel that review session really helps, you want something extra help, you're welcome to come and sit in that. Is that reasonable? Again, it's not a requirement. It's not that if you sit in that you will gain something. That's not true. But it will be a refresher for you. It will help you with. Does that sound reasonable? Okay. We start on a new concept today, a significantly different concept, and that is the idea of magnetism. And you will see that, try to see analogies between what we have studied in electric field and magnetic field. There are differences, there are significant differences, but still, mathematically speaking, you will see a lot of similarity in the two. And let me, since there is an analogy there, so let me remind you whatever we did for electric field, now that we have spent some time on it, so hopefully it will be a good idea to have an overview of what we went through. So the first idea was this is electrostatics. Electrostatics. The first was the charge. Electric charge. Let me call it electric charge because we'll talk about magnetism. Electric charge. So just to have a discussion here, I haven't introduced it yet. So we have talked about electric charge, electrons and protons are the classic examples. You can have collection of electrons and protons, and you get a collection of charges. What is a magnetic charge? Have you come across what is a magnetic charge? Any comments? You all have come across magnetic field, correct? Magnetic field in some form you see it when you think of a refrigerator magnet, something that sticks onto that. That's a magnet. It creates a magnetic field. And so the question is, what creates the magnetic field? What can you associate with the magnetic field? The magnet itself, what does the magnet have? Dipoles, what dipoles, dish dipoles, magnetic dipoles. Yeah, so the answer is magnetic dipole. So a magnet typically probably in your elementary science courses, elementary means most of the science courses, even in one, you will represent a magnet like this. Right, that's a typical magnet, and the magnetic field is like this. Compare this to the electric field, that's symmetric. On the left side, this is what we mean by a magnetic charge. One of you said it's a dipole, so dipole because there are two magnetic charges that is there inside a magnet, so you call it a magnetic dipole. A magnet that we typically see around us is technically a magnetic dipole. We are talking about an electric dipole, positive and negative charges together. That's an electric dipole. This is a magnetic dipole. This is the analog of a positive charge. North pole, we call it North pole. A magnetic charge is basically North pole. So I asked the question, what is a magnetic charge? We mean the North pole in there. That's a negative magnetic charge. We call it the South pole. If we break this magnet into two, what do we get? Can we separate the North pole out and then South pole on the other side? If you break the magnet, you get a North pole on one end and the other side. So if you break a magnet, how does it behave? Does it behave any differently? Right. So you break it, it turns out that you again get a North pole, South pole. You broke it. You again get North pole, South pole. What if you further break it? It turns out that as of today, we have not been able to separate the North pole from a South pole. It has never been possible as of today to be able to separated, and for all purposes of this clause, we will assume that north pole doesn't exist on its own. It always comes in combinations with south pole, so they come together. So to our knowledge, as of today, even though theoretically there are reasons to believe that they exist, but for all our purposes, they don't exist because experimentally it has never been possible to separate them. So a magnetic charge doesn't exist on its own, but it's necessary to put it together with a south pole, and it is always the dipoles that come. It is like saying that a positive charge, a proton doesn't exist on its own, it always keeps together with an electron, and an atom cannot be broken apart further. Then you would say that electrically also that's not possible. But in electrically speaking, an atom can be broken into a positive charge and a negative charge. But magnetic properties apparently it cannot be done. So that will play an important role in here, and that would be a difference between the two. And that immediately you would ask that what are the sources of magnetic field, and that would be one of the points we will consider. But again, going back to electrostatics, that electric charge and the positive and a negative charge. Let's talk about a positive charge. Electrostatics, you can have a positive charge. So that's just an electric charge. So first you have an electric charge. The second concept we said is this creates an electric field. I'm talking in terms of logically distinct steps. It doesn't happen in chronology in the sense of it's not that in time you have first a positive charge, then it waits for some time, and then it creates an electric field. The moment you have a positive charge, it comes with an electric field. So this is the logical breakup of the concept. So electric charge, then it creates an electric field. An electric field is electric charge, and that's how an electric field has been represented by it. That's electric field, and this is the field. And the electric field this creates is equal to Q over R squared. And then there is 1 over 4 pi epsilon naught. And this, remember, is the electric property of vacuum. We call it the permittivity of vacuums. And that is an R hat, which represents the fact that this is radially outward. Okay. So again, that is a charge that creates an electric field. And the third idea is to leave some room here. Third idea is that there is an electric force. But an electric force is again logical set in the charge. Creates an electric field, and this electric field exerts a force on another charge. So another charge in here is positive, that exerts a force. So maybe keep it along that line. If I have a positive charge here, in that line of the electric field, it exerts a force which is equal to Q1, Q2, equal to Q2 times the electric field created by the first one. That's your conceptual breakup of whatever we did under law of electric charge, create electric field, exert a force on another charge. This can be energetically described. We describe what is we use the idea of potential energy and electric potential, and we have constructed electrical components associated with it. A very similar concept is instead of electric charge, talk about electric dipole. Let's see, this an electric dipole is negative charge and a positive charge. negative and a positive charge, they are significantly close to each other so that geometrical distinction between the two is not there. If you're very far away, they look like a neutral object, right? So this, think of it as a single object, that's an electric dipole. The electric field due to that will be negative, positive. Its electric field starts from the positive charge and comes to the negative charge, and they look like this. And it starts from positive and goes to negative. Always electric field originates from the positive charge and goes down into the negative charge. An atom, a neutral atom, is very much like this, a positive and a negative charge, but they are so confined to each other. As we get closer and closer, they are pretty much superimposed, and what we have is just this. So an atom will have an electric field like this. It will be significantly weaker also, and a charge has an electric field like this, significantly different. So the source of the electric field due to an electric dipole and an electric charge is different. And if you put a positive charge here, you would argue, oh, this positive charge is going to get repelled by this charge, it's going to get attracted by the negative charge, so there could be no force at all. No, there is a slight distinction, so this force is slightly farther, so it is weaker, and the force is in this side. Very counterintuitive, right? So both are pulling it in that direction, but the force is effectively in that direction. And that's the vectorial nature of that force. And now the challenge is, or the problem is that in magnetic case, there is no equivalent of electric charge. There are only magnetic dipoles. Otherwise, most of these concepts remain very similar. So whenever we think of a magnetic field, we are bound to think in this term, because this is the basic object that exists to create a magnetic field. So that's going to be the overall picture, but we want to build this slowly. So we are going to pretty much do the reverse. We talked about electric force later. First, we talked about charge, then create electric fields, then create an electric force. In magnetism, we will do the opposite. We will first assume that there is a magnetic field. We don't introduce it at the early stage because it's slightly more complicated than the electric charge. It comes out to be more straightforward to start with the force idea. So we will work with this and then talk about what creates the magnetic field. So that will come later. So we'll start by saying that there exists a magnetic field. What do you mean by a magnetic field? And it's the thing, if you want, the entity. If you, when you're carrying around a magnet around, it pulls another magnet. So what is that in between? That's what we mean by magnetic field. It is not visible, it doesn't occupy space, very much like electric field. It's not localized, it is spread everywhere. You might have heard popular language, things that permeates all through space. A magnetic field and electric field are classic examples that do not occupy space, but they have energy and momentum. So they permeate anything that does not occupy space, but still has energy and momentum. They will permeate all over space. They will go all the way to infinity. It exists. A component of an electric field due to a point charge exists even at infinity. Gravity is also exactly like that. The gravitational field of Earth can be felt all the way at infinity. Only there it dies off to zero, even if you're very slightly, how much ever far you go, you cannot escape gravity. It is weak, but it always exists. So that's the okay. So our basic idea would be that there is a magnetic field, and what the force exerted by the magnetic field. So we'll talk about magnetic force. And the idea is that if there is an electric field there is an electric force, and the electric force was very straightforward. Just multiplied by charge. In fact, visually speaking, it just flows in the direction of the electric field. So very intuitively obvious sort of, if the electric field is imagined to be a flow of water, if you put an electric charge in it, it flows in the direction of that. Intuitively very obvious in fact, but magnetic field is not like that. It is counterintuitive, and this is how it works. And it's going to be three-dimensional, so we have to bring some notation. So we are going to have the magnetic field represented like this. This is going into the page. That's going into the page. And the magnetic field will be represented by the letter B. Magnetic field. And B was for electric field, magnetic field. And we're saying this is a uniform magnetic field. So let's also say it's uniform here. Uniform because they're equally distributed. The notation we will use is a circle with a point in it. This is coming out of the board. And a circle with a cross in it going into the and mnemonic to remember this is that if you have an arrow, traditional arrow, which has feathers attached to that, when an arrow is coming towards you, what the first point you see, if you were to just try to imagine what the very closest point from the arrow, that will be a point, right? It has a pointed arrow, so that's the arrow head of the head of the arrow. This is the tail of the arrow. Typically, there are feathers attached to that, and this might be a representation of that. So that's just to make you remember what is what. After a while, it can be confusing in one. It's very much like right and left. It can sometimes it can be confusing for some people. So this is uniform. No, uniform. So this is uniform. The magnetic field is going into the page or into the board. And if it was the standard picture of the analogy was like electric field, if I put a charge in here, if it was to affect it all, now notice what we are doing. Electric charge is a concept of electric field. But now we are saying, what is the effect of the magnetic field? You're not talking about the effect of a magnetic field on a magnetic charge. Instead, we are talking about the effect of a magnetic field on an electric charge. So that is a mix of concepts here. And what is going to happen is that actually the electric charge itself is going to be the source of the magnetic field. So we will try to give some interpretation of what North Pole is, what exactly creates the magnetic field. The answer is that a moving electric charge is going to create electric field. So maybe that's a good thing to write down. It's a concept we want to keep. It will help in understand. So right. So electric charge creates electric field. I think that's okay. Electric field and started into electric field. So what creates a magnetic field? A simplistic answer is North Pole, but that's probably just a word. You don't get a feel for at a microscopic level what is happening. So how is a magnetic field created? Moving. So this is Q, right? Q creates an electric field. The difference is moving. And moving electric charge. That's why we insist on using the word electrostatics, right? It's only when the electrons are at rest that is applicable. Moving electric charge creates magnetic field. magnetic force, doesn't start with magnetic field. So here, moving means velocity, right? Q times V. Q times V creates a magnetic field. So this will be the connection. The way charge is connected to an electric field, a moving charge is what creates a magnetic field. And similarly, magnetic field will affect a moving charge. Magnetic field will not care for a charge. If you want to escape from magnetic field, if you feel that a magnetic field is very dangerous, if you want to escape it, stay at rest. It is insensitive to velocity. It cannot exert a force on you the moment you come to a rest, relatively speaking. So the magnetic field has a source that is moving. If relative to that, you're at rest, immediately the force goes to zero. Very counterintuitive. It's like saying you are moving in a river, and if you start moving at the same velocity, the force suddenly will cancel out and you stop flowing. So if you want to stop flowing in a river, you get relatively at the same velocity. It's not counterintuitive when it comes to imagining what happens to you in a flow of river. So moving charge creates a magnetic field. Another way of looking at it is that moving charge has this q, velocity has a distance over time. Q over time is the current. Another way of creating magnetic field, the same thing, it's the same movement, but it is the length. A movement of charges is nothing but current. So current is what creates a magnetic field. If you want to create a magnetic field, how do you go about in the lab? You take an electric wire connected to a battery, there are charges moving around. A moving charge creates a magnetic field. Anytime you see a wire close to that, there is a magnetic field. Next time, take a magnet and take it close to an electric wire, it will move. Like a magnet gets affected by a magnetic field, so it will move. So those are things that will come out of what we are studying in this two lectures. So again, coming back to introducing the magnetic force, magnetic field. One more thing, I need to specify the unit. A new concept, I need to talk about what is the unit of magnetic field. It is Tesla. TES. And then you ask, what is it in terms of basic units? Newton is with the programming basic units, so Newton over charge Coulomb, and then that is meter per second. But for our purposes, it will just be Tesla. You can simplify this further. Newton is 80 meters per second square, and you can simplify that further. Okay, so what is the force exerted by a magnetic field on a charge? So that's your positive charge we want to talk about. If it is just at rest, so these are some of the facts. If it is just at rest, if the charge is at rest, there is no force. The force is equal to 0. So rest implies the force is equal to 0. That immediately tells us that it has something to do with velocity. That force must be having velocity in it, because only when things are moving there is a force on it. So it is necessary that it moves. So you have to introduce the velocity v. If it's not moving, there is no force on that, or there is no magnetic force, I should say. And let's also specify this is magnetic force. Magnetic force. For some time, you'll be working with magnetic force often, you will not see the subscript. Next, let's say what is the force in here? The force turns out to be perpendicular to this V and the V. So that's the direction of the force. And how do you come up with that direction? V was here. What's the rule that tells you that that's the force? So this is a cross product. The force on a magnetic charge is equal to the charge itself, this charge times the electric field. But remember, in magnetism, whenever you have a charge, you have to replace it with a moving charge. Charge gets replaced by moving charge. So this is velocity of the current. It's a moving charge that is important. And that's what gets affected by the magnetic field. That's your expression for the force. But that should be bothering, right? What is missing in here, or what is wrong in this expression? Is the right side a scalar or a vector? Right side? Vector, but there are two vectors there. So how do you, I had to specify the operation between two vectors, right? When you're multiplying two vectors, you can multiply them as scalars. That's a dot product. Or what's the other multiplication between vectors? A cross product. And the left hand side is a vector. So I want to use the cross product. So that's the counterintuitive part. It uses the cross product to get the of the nature. This decides on what the force on a moving electric charge by a cross product between the velocity or moving charge of the movement and the magnetic field. When it comes to magnitude, so that once you have a vector, I need to be able to calculate what is the magnitude of that vector and what is the direction of that. So first let's talk about the, let's talk about the direction, and then we will come to the magnitude. Okay. So the direction, let's think of this as any cross, right? These are three vectors. C is equal to A. B is not a good example. A cross C is equal to B. You haven't come across this letter, I suppose. Yeah, B. So some random three vectors. And how do you get the cross product between them? Let's say this is your A. That's your vector A. In the field, there is a whole set of lines that represent a vector. It's called a vector field, but here that's just two vectors. Right? So that's A and this is C. And the question is, what's the direction of B? I'm not worried about the magnitude at this point. What's the direction of the vector D? So you want to use what is called the right-hand rule. This is how a cross product works. It's necessary that you use the right hand. You might be, most of us use the right hand to write. So you want to stop writing and use that as your for determining this direction. Right hand, first point of fingers in the direction of the first vector. So that's the 4 fingers you point in the direction of A. And you will see that there is a lot of arbitrariness in there. That's also pointing in the direction of A. That's also pointing. So there's a lot of freedom in there, but it's all axial. You can rotate your hand like this, but you have to keep your fingers pointed in the direction of A. Now we want to take away that movement restriction by pointing in the direction of A in such a way that your palm is facing C. You point in the direction of A such that the palm is facing C. And in that position, now that you have stopped your movement, there is no constraint there. At that point, you open the thumb, right? And say that that's going into the bowl. So A is your 4 fingers. C, point or palm points, faces, faces, C, and D is the thumb. That's a mnemonic if you want to remember this. There are many other ways of remembering this. You can think of a right hand with the 3 fingers opened out, perpendicular to each other. Then the first finger points in the direction of A, and second finger points in the direction of C. And when you stretch out the thumb, that gives you the direction D. So that's one way. Or else you point in the direction of A and then curl your finger in the direction of C. That's one of the popular ones. And while that is doing that, what is the direction of the thumb? Look it up. Your textbook has a couple of methods to do this, but if you search on Google, there are innumerable number of ways to do that. Choose your favorite one. Doesn't matter which one you have, but if you have none of them, use the one that answers the thing. That's good enough. Or if you even algebraically, you can do this using the ideas of what is the cross product between I hat and they hat and K hat. So that's the idea of cross product. And if you want the magnitude, so again, direction, so direction of D, direction is using right hand rule. Technically, in principle, there is only one right hand rule, that's sufficient, but you will often see in books that there is a right hand rule 1 and right hand rule 2. That's convenient, and we will also talk about it. But technically, mathematically speaking, there is only once you choose your rule, and the rest everything should follow from there. But for convenience, later on we will say what is called a right hand rule number 2. It's convenient, and we will also use that. There's nothing wrong in that. But realize that at the basic level, there is only one choice. And what's the choice in here? I could find that out. The choice is if you have chosen X here and Y there. And if I ask you what is at the very first time, if you happen to be independently sitting on an island and developing your coordinate system, and half of you might choose B coming out and B going in, there is nothing wrong in either one of them. That's a notation you have fixed. But there is a difference between the two. Physics, it's some part of physics can be different in the two coordinate system, especially when it comes to mirror. In a mirror, things look different. Your right looks left, right? That's dependent on this. Whatever this choice you take, that's dependent on that. So the notation is almost consistently all over time. The rare occasion that everyone agrees on something, that the Z is coming out of the road. So it is X hat, if you use these as vectors, always X hat crossed with Y hat is what we see here. If it is going into the boat, that doesn't work. So that's a uniform notation that works out. And this plays an important role when you're analyzing what happens to your right hand. Why does the image inside the mirror lift the left hand? Inside the mirror, if you think of a world inside the mirror, there is a geometry associated with how things are moving inside the mirror. That's a good problem to analyze. If something is moving on your bathroom counter, how does the motion look like inside the mirror, especially when it comes to rotations? We have an intuition for guessing what will happen. Right? And you will notice that whenever things are rotating, your guesses will be wrong. It is very counterintuitive what happens inside the mirror. You say it's a right-handed world and a left-handed world, and that's because inside a mirror, X hat cross Y hat is minus Z hat. Most of the planar geometry, projectile motion, linear motion, everything looks the same. What will look different is circular motion. Circular motion depends on this cross product And there you will start seeing differences. Whatever is going in a circle, how it affects something else will be slightly different. Slightly means there will be a negative sign effect inside the mirror. So that's something you can analyze on your own. So that's the direction. It has this feature of the cross product, and it is given using the right hand rule. What about the magnitude? A vector has a direction and a magnitude. Magnitude of f of b is simply, so when I don't write the vector sign, that means it's the magnitude. So it is the magnitude of the moving charge. So v, the speed comes into picture, not talking about the direction, speed, and it depends on the magnitude v, b, and the sign of the angle between them. That's the angle. That's angle between v and b. The movement is described by velocity. The magnetic field is described by v, and there is an angle between them. In this particular scenario, magnetic field is going into the boat. Velocity is in the plane of the boat. That angle between them is 90 degrees. Right? That's a special case when, and that's a simplicity also, in the sense that that angle is, whenever it's 90 degrees, sine of 90 is 1. So the effect of this is significantly diminished in that particular case. The sine of 90 in that particular case is equal to 1. So that's a very specific choice, not necessarily always true. So magnitude is given by that. But often it is convenient to do both this algebraically simultaneously. So let's say that velocity is equal to v1 in the I hat direction plus v2 in the j hat direction, and let's keep it very general that it is coming out of the board also, and that's v3 in the k hat direction. So these are geometric ideas. You have magnitude and direction, and you should be able to do this cross product at an algebraic level. If the magnetic field is v1 and it has v2 hat plus v3 k hat. What is your force? Will be equal to charge times this. So it is q times v1. So the first, when it is the direction in along I hat, I start with, if I'm interested in 1, I go with 2, 3. Notice the cyclic property here. That is 1, 2, 3. Like that in a circle. I want the first component, so it is 2 times 3, and it is directional. So the first component is given by 2 multiplied by 3. So notice how I'm going to do this. Q times v2 times v3, 2 times 3, and then I flip it. 2 times v3 times v2. That's the algebraic rule between the first component of the force. The second component is going to be, second is this. If I want the second one, I start with 3 and multiply by 1. So it is q times v3 and v1, and then flip it and put it on the negative sign. It's q times v1 times v3. That's the hat. And do the same thing once more. That's plus k hat will be, so it is 3 now, 1 times 2. It is q times v1 times v2 minus of q times v2 and v1, and that's k hat. This is a very general expression, algebraic expression, very powerful, but has less intuition, too many variables, right? Most of us in the beginning CAD work only with 2 or 3 parameters. More than 3 parameters, it gets very hard to analyze. So this is too much, probably. for many of us. So that's very powerful algebraically, but geometrically, it's a lot more powerful to have direction and magnitude. But we will work with both. It's expected that we know both, and most of the time when it comes to algebraic expression, then things will be happening in a plane. Things is happening in a plane, all of this will be zero. But one should be having the practice of doing this. There's a mnemonic to get this expression, get this permutation expression, and that is by writing f of b as I have, they have, they have, and then there's a q times b1 moving charge, q times b2, q times b3, and then you write b1, b2, b3, and then you take what is called the determinant. The rule is that when you got the I hat, you multiply these two. This times this minus this times this. That's the first expression. When you want a j hat, get rid of the column that has j hat in it. b1 times b3, and then b1 times b3. Except that every alternate one you want to use a negative sign there. So if you want to use that, it will have a negative sign and then you flip that. Either way, you can remember whichever you want to. So that's the algebraic way of getting the magnetic force. But that's okay. So now we have a statement for the magnetic force. What really happens to the star? So I've given you an algebraic expression, a total complete expression if you know the vectorial form of the velocity of the charge completely, and you know the magnetic field, whatever complicated structure you have, you can calculate the magnetic field. Intuitively, it is magnitude is given by this, and the direction is given by that. So what really happens to the star? That's what we would be interested in. What do we see about the star? Here, a charge in an electric field just flows, right? Intuitively, it just flows in a magnetic in an electric field. What happens to this? So let me go back, and so that is a charge, moving charge in a magnetic field. What does it do? We argued that the direction of this is in this direction, right? Perpendicular to it. So I'm moving in this manner. The magnetic field is going into the floor, and I get pulled that way. It's very counterintuitive. Someone is pulling me down, but I am getting pulled to the to my right. So that's the idea of cross product. But nevertheless, it is getting pulled that way. Whenever you have a force acting to my left, I will start moving in that direction. Force has to have an acceleration. I will start moving this way. Like to change my velocity. That's my new velocity. But now the force has changed. The force will again be perpendicular. So that's my force here. And again, I will start moving to the left and here in the next instant. First instance, I was here, I get pulled, I moved a little bit to the left, I keep getting pulled. And if you analyze this perfectly, this actually will go in a circle. So the take-home message for this whole lecture, or for what happens in a magnetic field charge, is that they start going in circles. A positive charge in a magnetic field starts going in circles. That's what it does. That's so the whole white Earth moving around the magnetic, around the sun in a circle. Same reason there is a force in that direction, but there it is not the cross product that comes in. In a sense, it is, because acceleration in a circular motion can be written in terms of angular velocity. So there the origin of the circular motion is entirely different, but conceptually there are similarities in there. So what happens again to a moving charge in a magnetic field? It starts moving in circles. And the moment it starts moving in a circle, the two information you need is what the radius of the circle and how much time does it take to go in the circle. Those are the two information that is relevant or important for a process of, for our intuition as to what happens to a charge or moving charge in a magnetic field. And let's try to investigate that. And this requires a little more detail in here as to how exactly is it perpendicular. You might not be convinced that this is exactly perpendicular all that, so I have to use the geometry of a particle going in a circle. So I am going to make a statement here that it is a circle, and it becomes an homework exercise as to you fill in the fact that actually a charge moves in a perfect circle. In your homework, you do have such an equation. We will do that algebraically. You will solve a differential equation to show that actually it is a circular motion. So that's a more of a completeness for the logical steps to be complete. You have to be sure that actually that's a circular motion. So from this point on, I will use the fact that in a magnetic field, the motion is circular. So in this particular situation, because the magnetic field is perpendicular, that sine of theta is 90 degrees. So we have NA, which is equal to force, right? There's only one force we are talking about here, that's the magnetic force. Remember your Newton's law tells us that mass times acceleration is equal to the vector sum of all the forces acting on that mass. It's a vector sum of all the forces, but there's only one force, so it is the force due to the magnetic field. That's this. This is a circular motion, so the magnitude is v square over r. Remember that whenever something is going in a circle, there has to be an acceleration. Acceleration is towards the center of the circle, and its magnitude is given by v square over r. That's the magnitude. That thing is radial inward. That's radial inward. So this is radial, and minus sign means it is radially inward. So this means this together means that it is radially inward. What is the magnetic force itself? We said is, again, if it is 90 degrees, it's radially inward, that's minus of x, and it is Q times V times V. The radial inward part cancels out, so we are interested in the what I asked was what is the radius of the circle and how often is it going in a circle. Whenever something is going in a circle, there's a time period associated with it, which means that how often is it going in a circle, going around in circles, or the periodicity of that motion and the radius of the circle. Those are the two properties of a motion in a circle, and you can get that from here. So let's see. So there is a V that cancels out, so these two don't exist. So V cancels out, and we have mv over r. But remember that velocity in the circular motion is omega over r. Or you can say this is no, that's wrong, right? Wrong. Sorry. Omega times r. It is 2 pi r, the circumference, over the time period. 2 pi over t is what is called omega. So omega is 2 pi over t. The measure of frequency. Frequency is 1 over t. And omega is also 2 pi f. Remember your circular motion concept. If something is going in a circle, there is a time period has a frequency associated with that 1 over the time period, and the angular frequency, when you measure the frequency in angles instead of how many times you're going in a circle, that is 2 pi times the frequency, and that's what is called the angular frequency. So velocity is nothing but omega r, but this is v over r. So what you're getting here is that mass times frequency, angular frequency is q times b. So how many times it will go in the presence of the magnetic field is given by the ratio of q over m times b. This is a very special property of circular motion around a magnetic field. It depends linearly on the magnetic field, but notice it depends on the charge to mass ratio. right? We saw that similar concept earlier also in where things depend on the charge to mass ratio. This is called the cyclotron frequency. Immediately you can think of the fact that if it was a proton versus an electron, whenever there is a mass dependence, this mass is much heavier for a proton, right? An electron, this is much smaller. The heavier means frequency will be smaller. So how many times does a proton go around a magnetic field versus an electron? It will go less number of times. Electron will really go fast around a magnetic field, but a proton goes less frequently about, not less frequently, less number of times around the magnetic field. Remember, magnetic field is a flow of light, so there is no one line that has to go through. So wherever it is, the moment you start moving in a magnetic field, you start going in circles. That's the way to look at it. If you are charged, the moment you move, you start going in circles. It doesn't matter where you are. There is magnetic field everywhere. It permeates all over space. So the moment you move, you start getting twisted. So there's a gyroscope effect in there. And this comes from a simple Newton's law. The moment you write down Newton's law, you can immediately conclude that there is a frequency associated with that. And once you have a frequency, we can talk about the radius. Radius depends on the velocity, how fast you're going. So that's universal. This is depends on very fundamental properties and the magnetic field alone. So this is a very a property that depends only on the magnetic field. Here, it depends on how fast you are going. So it depends on your design. If something is moving faster, then the radius will be smaller or bigger, right? So V, what did I write? R is V over omega. V over omega, and omega itself is Q over M. So it is V times M over Q times V. This is less interesting because there are two parameters, right? The moment you have two parameters, then the analysis becomes harder. But here it is very proportional. So it becomes essential if you ever want to design a test sensor, and if you have a sensor that can measure your omega, these are the quantities you want to look for. A quantity that depends only on one parameter. That's a perfect sensor you have for a magnetic field. That doesn't mean that that might be the best sensor to build for a magnetic field, but that's a relation that is very useful. Okay, so that's overall the point. The message you want to take home again is a moving charge in a magnetic field goes in circles. Its frequency, how many times it goes, is decided by the magnetic field. It's proportional to that. Its radius is inversely proportional to the magnetic field, and it also depends on the velocity. There is a very beautiful effect associated with this, and let's discuss that for a moment. And in that process, I will also calculate exactly how much is the angular frequency and the radius for an electron and a proton moving with a certain velocity. So this effect is called, let's see, the simpler northern lights. Thing is called aurora breathing. I can spell it. Check for the spelling, not her. Have you ever heard about northern lights? Yeah, so a good number of them. It's a effect you see in the sky. It's not very common in the lower latitudes. By lower latitudes, when you're closer to the equator, it's not very common. You have to be very much towards the Arctic Circle. And why is that? Very simply speaking, it is associated with the Earth has a magnet itself, so we'll talk about that in a minute. And the Earth's North Pole is somewhere close to the geographic north, but that's not the same. So that's the color in a minute. So what is the effect if you are in the northern latitudes? When you sometimes in the night, sometimes not always, you look up in the sky, the whole sky is greenish in color, greenish blue, like there is a yellow, there is a, it's very colorful, and it is, from what I hear, it is like a curtain, it's a shimmering light, so it's very effective kind of light. And if you've not seen it, it is not very easy, even if you go to a northern place, it may not happen on that particular day. So it is very hard to, you got to be very lucky in that sense. Sometimes, very rarely, it shows up in regions, northern parts of US, like sometimes in Minneapolis. But again, all this is from what I've read. I have myself not seen it. I've lived somewhere in the north for 2 years, but I was not lucky anymore. So it's rare event. So you see, lucky. So how does this happen? So let's try to understand that from here. So first thing is that Earth is a huge magnet. Our Earth, it's a huge magnet, and that should already raise a question for you as to I said there has to be a moving charge to create a magnetic field, and what is moving inside an electric field? We seem to be very neutral, right? Earth effectively from a global perspective is a neutral object, so it's not a moving charge, but effectively deep inside the Earth, because of the heavy pressure of gravity, there is so much of compression from the mass outside, things get very hot, and when it is very hot, effectively, it's a very good conductor. Deep inside in the Earth, it's an extremely good conductor, and it is in molten form, so that is a motion associated with it, because mostly associated with the revolution or the rotation about the axis of Earth. So because Earth is rotating, things try to rotate everything inside that as a rigid body, but it is molten inside in the deep part of our Earth. So it is not as easy to move that as it is. That is a differential element. So the outside part is moving faster than the slower part. Nevertheless, the point is that there is a relative motion between 2 points inside, and it's a moving conductor. So effectively, there are charges on a conductor, and the conductor is moving. So it's a rotating conductor, and a rotating conductor can create a magnetic field. So that's effectively very simplistically speaking, and basically that's why Earth has a magnetic field. Most of the planets which have a molten metallic structure deep at the core will have a magnetic field. If it does not have, that means it probably doesn't have a metallic core at the center. Like there are planets like that, but very rare. Most of the heavier planets will have a metallic core, and it has a metallic core because of gravity. It is molten, and because of the molten structure, as a conductor that is moving, and on the prove that a moving rotating conductor will have a magnetic field. Now, what you need to take home for our purposes is that Earth has a magnetic field. Then you ask, it's a magnetic field in the north and the south, right? So where is the north pole of our Earth, and where is the south pole of our Earth? For reference purposes, that's our geographic north. By that, that's the Arctic circle. The Arctic is north. So that's the south pole and that's the north pole. We have the geographic north pole and the geographic south pole. That's going to be different from the magnetic north pole and magnetic south pole. And the magnetic north pole is nowhere close to the north pole. It's in fact close to the south pole. So somewhere here. So that's your geographic. Let me label it here. Magnetic north pole. It's slightly off from the south pole. It is off by about 11 degrees or so. And where is it in the south pole? That's somewhere here. Notice that it is not a unique point, or it is a unique point, but it is not On a two-dimensional picture, I cannot picturize that very precisely. The moment you say it is 11 degrees with respect to the North Pole, there are a lot of like the whole circle which makes 11 degrees. So somewhere on that circle is the South Pole, and it is in Canada. It is in the very northern part of Canada. That's where the South Pole is. So if you want to have the maximum effect of the magnetic field, be on the South Pole, you go all the way to the northern part of Canada, and on this side, it is somewhere in Antarctica. You don't have great civilization. So the only choice you have is to go to the north and go all the way to the northern Canada. This is your magnet now. It is tilted with respect to our northern and geographic north and south. And remember, North Pole is it creates magnetic field. That's your magnetic field. Goes like this. So all the magnetic field enters into the northern part of Canada. That's the basic idea. And that's why it is called the North Pole, because all the lines are going there. And how do you know this? If whenever you want to detect the magnetic field, we have talked about how a positive charge gets affected. And the simpler effect associated with the magnetic field, but mathematically difficult part, that's why we are not introducing it here, is how a magnet points in the direction of a magnetic field. If you take a refrigerator magnet, and hang it on a thread. Let's say that it is not straight, and most of the refrigerator magnets are not spherical in direction. They have a north and south pole. You tie it on a thread and let it hang. It has a directional nature to that, and it will always point in the same direction. And it varies that direction, that's the north and south axis. It will always point there. That is the idea of a magnetic compass. Before GPS came in, these days we use the phones to do that. In fact, a phone has a magnet inside. That's the only way it can detect the magnetic field. So it uses a magnet inside. It's a very sensitive magnet, but a refrigerator hanging off a string is a very crude magnetic compass. It's a very crude GPS, but it does the same job. It points to the north. So whenever since anything points to the north, you say that that's the North Pole, but it's actually the fields are coming in, so it's actually the South Pole. So that's the north, that's the cause of that nomenclature issue. And nevertheless, that's your magnetic field, that's your Earth. And what is the strength of the magnetic field? Earth's magnetic field. Magnetic field due to Earth. It's good to have this will serve as a scale. This is how much it is easy to generate so much of magnetic field. It is 10 raised to minus 4 Tesla. We often say just T. Since it is so important for us, we live on Earth. 10 raised to minus 4 is too much to write, too much to say. We create a new vocabulary. That's one goal. But this is the standard unit. We will work in Tesla. But 1 joule is pretty much 10 raised to minus 4 Tesla. Where else do you get a very strong magnetic field? If you ever had an injury and you had to check, you had to do what is called an MRI, like magnetic resonance imaging, that's what it stands for. But MRI, when if you have ever been there, hopefully not, only you must have gone through a painful episode, only then you get a chance to go in there. So it's a huge tunnel-like structure, and you lie down and you are taken into that. That's a huge magnet. That's a huge magnet. That ring that you see around, that's a way to create a very strong magnetic field. That's pretty much the strongest magnetic field you can see around us here on Earth. Strongest is about 10 times, only about 10 times larger than that. So that's about 10 raised to 4 times this. So it's about, in an MRI, the magnetic field is created about 1 Tesla, that's a 3 Tesla. The maximum you can do is about 10 Tesla. Very hard to create large magnetic field. Having said that, in the universe, when you go at close to binary star or neutron star, you can get extreme, stupendously large sizes of magnetic field that we're talking about the 10 for. But for our purposes, even to get 10 Tesla is very hard. So if you have a good way of a clever way of generating magnetic field, that's something you want to check out. Okay, that's a magnetic field, and we have sun, right? So now we want to talk about northern lights. So that's sun, and I have 3 minutes. So that's sun. Sun is also a magnet. It's a much stronger magnet than the Earth. Anything that is heavy, I said, because of gravitational pressure, will melt everything inside the deep core. And the moment you have a molten metal, then it starts, as if the sun is moving or rotating, then it will create a magnetic field. It's a significantly larger magnetic field, so this is your magnetic field. But very close to Earth, it is our magnetic field that dominates. So when we are moving around the surface of Earth, even though sun, there is a magnetic field associated with that, it is our magnetic field that dominates because this gets weaker. So this has a magnetic field in here, so it bends, it goes around. So it bends and goes around. So in our small pocket, that our magnetic field dominates, right? Because we are so far. But nevertheless, sun is a flame, right? It's a fire. Fire has too much energy, things can go around, it breaks apart all atoms. That's a simple way of looking at it. Things are moving so fast at high temperature that it breaks apart all positive and negative charges. So whenever there is a fire and emits a flame here, we call it corona injection, there's a lot of positive and negative charges. They're already separated, they're not atoms, they are ionized atoms. So there's a positive charge and a negative charge, and there is a lot of magnetic field. What does the positive and negative charge do? They start going in circles around the magnetic field. So they go along with magnet, and they get drifted also. So they go around with magnetic field, they switch over to this, if these lines slowly get into this, and they all get drifted and they all come to Canada. Right? So they all the charges that is coming from the corona from a sun, which can hurt our electronic components, they are most likely to get affected in Canada. So if you have a very sensitive electronic device, you don't want to carry it to Canada, but that is exaggeration. It's not so dangerous. I'll stop here and we'll talk more about this on Thursday. Thank you.